Hello, in this video, we'll be discussing latches and flip-flops. They're essentially the same concept with slight differences. From latches and flip-flops, we can construct larger circuits such as shift registers. I'll also be talking about specific kinds, what they're used for, and how to use and construct them in circuit simulators. So what is a latch exactly? Well, it's a circuit that can hold a single bit of data until a new signal changes that. Now, keep in mind a bit is a binary value. It's 0 or 1, on or off, true or false. So this is what we mean by a single bit. We're not talking about a holding an analog voltage value or anything else. A minimal latch has one input, one output, but it often has more than that, really depending on its type, subtype, and actual physical implementation. From what I've been told, it's a latch because it can be set and reset, or or reset or changed. Much like a latch mechanism on a door, it can be either opened or closed, but it can't be both. The state is temporary, at least in terms of a physical implementation, at least until the power is turned off, but the structure is also present in non-volatile memory as well. It can be represented in a number of ways, from actual dedicated latch symbols to using a combination of logic gates or even using discrete components or ICs. A latch, by definition, doesn't work on a clock pulse and it simply changes with a new input signal, although this doesn't stop latches from being called flip-flops and flip-flops from being called latches. We also have a concept of active low and high. A 0 or 1 could be represented as either in a circuit, so always check what you're looking to make or the data sheet or really whatever. Now, there are a number of types of latches beginning with the SR latch. And as you probably can guess, this means set and reset. It's the simplest latch with at least two inputs, set and reset, and probably two outputs, output and inverted output, although in theory, it could technically be one output. Allowing you to place it in one of these states is either set or reset. It usually can't handle both S and R being true and enters either invalid state or a race condition. By race condition, I mean there could be ever so slight difference between the two signals. Nothing's perfect. So whatever race is ahead gets set. And then there's a D-latch for data. Well, it usually has one input, effectively storing a single bit. It's basically on or off, 0 or 1. Then it provides an output and often an inverted output. A D flip-flop is sometimes still called a D-latch even though it has a clock pulse. A JK latch has two inputs, J and K, but unlike S and R, SR, it simply toggles its state if both J and K are true. So basically, a JK latch can be thought of as an upgrade to an SR latch, but both have different applications. T latch is a simplification of JK, where the J and K are shorted. So when T or J and K is true, then the output toggles and has two outputs, usually output and inverted output, although again, technically it does not need an inverted output. Any of the above latches can also have a gated version, which usually adds a second input that disables or enables state changes. This can be very useful if you're getting constant signals on the line. It's also possible for them to have clear or reset that erases the state of the latch, but as long as they don't have a clock pulse, they are technically latches and not flip-flops. Now, first we're going to discuss the SR latch, usually called the SR NOR latch. Why is it called NOR? Because it consists of two NOR gates linked together. This is usually the first latch that people learn, and this might actually be the first one that was described on paper. Set and reset at the same time. As I previously said, it creates an invalid state or most likely a race around condition. Whichever signal gets there first is the one that wins. It can be either set or reset, and it can ignore multiple set or reset signals. You can't open an open door. You can't close a closed door. Yes, there is a concept of fuzzy logic between the two, but ignore that for this case. It only changes when one's active and the other is not. Now, when you initially power up an SR latch in real life with a physical implementation, it could actually start in either state. And usually you want to factor that into your design. Now, if you're doing something like a simple IC model, you got something right here on the left. You've got a set, a reset, an output, and an inverted output. Um, Now, if you're doing this with logic gates, it's two NOR gates in this case, and there's a little bit of a truth table on the right. If both are set to 0, it just stays with the latch. That means it doesn't change. If set is low and reset is high, again, active low and active high, always consult your data sheets. Um, that means that output is 0 and inverted input is 1 because inverted is just the opposite. Set, same idea, but it's 1 and 0. And again, if they're both high, this says 0, 0. That means, basically an invalid state, but you'll probably have a race around condition. If you wanted to construct a set of discrete components, just you could put each NOR gate, just make it with transistors or whatever you're using and simply link the two. All you're really doing is the other output to reset comes from the output of the other. So basically, they're just linked together. The output of one is fed to one of the inputs of the other. So it's pretty easy to construct as latches go. There's also some ICs that provide SR latches. The MC 140, 43, and 44, they provide 4 CMOS implemented SR latches with a common enable pin. The SN 54279, I believe that's a 5400, provides 4 SR latches, and 2 of them have with each one having 2 set inputs. Um, the CD4043B that provides 4 SR latches that are all capable of tri-state logic, and they have a common enable pin. You'll see chips that either do a NOR or a NAND gate SR, so that you can simply construct your own latch as you see fit. Now, I mentioned the first one was a NOR gate. Well, you can also do the same thing with a NAND gate, and it's pretty much about the same, except it's with a NAND gate. Um, but you still get basically the same thing. All right, and then we move on to the JK latch. It's an improvement over the SR latch in one important way. When both signals are high, it simply toggles the output back and forth instead of providing for an invalid state. That's why essentially we see the SR latch on the right, and then we see this new part of the latch on the left with AND gates. There's not really any ICs, at least that I could tell, that provide JK latches that don't have clock pulses. There's plenty of ones that do flip-flops. When you just want to do a latch, they seem to suggest you just get chips that provide the AND gates and the NOR gates. And then you can simplify it even further with a T latch. You just short the J and the K together to form a T. And this simply toggles the output depending on the signal received. If it receives a high, it toggles it. If it receives a low, it doesn't. This example shows a clock pulse, which would technically make it a flip-flop. But if you just ignore that, then you can just simply turn it into a latch. Now, I've touched on gates, clears, enables, resets, etc. Gated latch, it just provides another input that allows you to enable or disable changes to the latch unless the gate is high or again, active low, low, and gives a little bit more functionality to the latch. Enable inputs are basically the same thing as a gate, so the terms are kind of interchangeable, but it really depends the implementation. You may see a lot of this on an IC, both called gate or enable. You've got your clear and reset. They're usually the same thing. Depending on the implementation, they might be slightly different. Like a reset might reset an entire circuit made of them. You might have a clear that only affects part of it. Um, and basically, as I said, it just allows you to reset. You'll see a lot of times you'll see a clear or reset signal on an IC, and they'll often affect all the latches or flip-flops on the IC, but you might also find them individually. So I've talked about latches. So what's a flip-flop? Well, this is not going to require a whole new set of slides. And there is some argument to what a flip-flop is. Some people would say if you're taking a latch and you're constantly changing its state, that makes it a flip-flop. I'm going with the definition that it only allows a change to its state on the edge of a clock pulse. An actual implementation, that pulse could be either rising or falling edge. I know I mentioned that in some previous videos, but clock edge is very important. It allows for it to be used as kind of a register or part of a register with a larger system so that everything is synced up with a clock pulse. Again, there will be people that argue with this definition and they're just as right or yeah, as this definition is. It's not necessarily something that's completely set in stone. Now, what is a clock pulse? Well, it's a pulse or trigger that synchronizes operation of a circuit. Its actual physical implementation um, could vary. An electronic device could have something as simple as one or several. Often, when you hear hertz being mentioned, they're really talking about the clock. So, I mean, the CPU could have one clock, the motherboard could have another individual cards, although there are ways for them to sync up, obviously, for a full computer to work. It really only needs to be a fairly narrow signal, a pulse or even just a trigger pulse. Data sheets will kind of tell you what values or that the value needs to be under a certain thing, like microseconds, nanoseconds, possibly even smaller than that when you're going into the mega or gigahertz ranges. Um, so always look that up when you're trying to use multiple things in a circuit. Easiest way to achieve this, especially for higher frequencies, is an oscillating crystal chip. You cut a crystal to a certain way that when electricity hits it, it oscillates at a very particular frequency. They can get this down very, very finely. The only thing is crystal chips usually need like at least 100 or 200 kilohertz going into the megahertz, and then obviously it goes higher than that. For any clocks that you want slower than that, you may have to just come up with a circuit. You might use a 5-5 timer or something else. Um, so yeah, the clock pulse can be associated with a number of different behaviors. Astable, monostable, bistable. But now let's take a look at every circuit and what we can do with that. So right here, this is just a basic SR latch. See what it does. Now in every circuit, it's just going to give an invalid state. It's not going to do, I don't think it's going to do any kind of race condition. Let's turn them off. Let's start them off, turning them off. So, oh, in this case, it does do a race condition. So we've got our set. It's not going to change no matter what we do. If we try to do both, it'll just give an invalid. Reset, it'll switch. There you go. That's pretty simple. We're doing this with two NOR gates. I'm adding the lights, that's why the resistors are here. Now here we've added a clock pulse, thus we've made it a flip-flop. All the clock pulse is we now have, in this case we're actually using 4 NAND gates. So this is a, NAND gate SR flip-flop. So we're doing this because we're adding the clock pulse as the other input to both of the first set of NAND gates. So we've got, well, let's turn them both to 0 and see what happens. Now again, it's only going to change it on the rising edge of the clock pulse. All right, so nothing. What about both? Okay, well in this case it's going to light them up both. But then it goes back to a race condition, and then it turns them both on, both off. Every circuit's kind of weird. So let's wait until we have a negative clock pulse. All right, let's see what happens. See, it's not changing it until the clock pulse. So that's the idea. Now here we have a JK flip-flop. In this case, we're not using logic gates. We're actually just using a stereotypical little IC here. See the clock pulse. Switch to 1, it'll switch. Turn that off. Switch it to the other, only on the clock pulse. Now, interesting behavior as we turn them both on and off. It'll just flip back and forth, and that's the key feature of the JK. Now we look at the D flip-flop. If this was a latch, it wouldn't be quite as useful as a flip-flop because you never know if it's several zeros or several ones in the way. But yeah, you could just remove a lot of this logic, some of the logic over here. But it's on a clock pulse. Right now it's set to 0, so it's not going to change. And setting to 1 is just going to pick one or the other. It's going to flip-flop back and forth. So 1, or I should say it'll be a 0, 1, so it'll be inverted or not. So we see the inverted here, we see the regular here. So yeah, pretty simple, but it forms the basis for shift registers, among other things. Now here we have a T latch formed from 6 logic gates. Basically, base both of our inputs, see, this is a toggle, so both the inputs have to go high for it to actually start switching. And it'll just switch it back and forth when they're both high, when you want to stop them flipping. So T for toggle. So nope, nope, but both of them, there you go, flips back and forth. Want it in the state it needs to be in, there you go. Now let's see what examples we have here in Falstad. Okay, so we've got some flip-flops and some stuff made from flip-flops. Let's look at the SR. In this case, it is a latch, but they're calling it a flip-flop. This is, again, one of the arguments. So they're both set to high, and it's I don't know if this is completely randomly. Yeah, okay, it's just random. It's doing it actually simulates a race condition. Now let me change the momentary switch nature of this. Whoops. Go. All right, let's reset this. Okay, see the race ahead. Let's set them both to low and see what happens. They're both coming out high. Okay. So we set 1 to high. Set to low, it gets that weird, they're both high condition. We do the other one, yeah, it seemingly has no effect. We'll set them both to low. We'll do high again. May not be behaving like it should. Oh, okay, that changes that one. Okay, yeah, that is working correctly. So let's see what else we have in store here. Let's see, sequential. We've got a clocked one. All right, so it's only going to do it on the clock. But the clock is fast enough here. See, we're setting the pulses and it's not changing. Now you'll notice the clock pulse actually shown here at the bottom. It's pretty small, so like when we were repeatedly doing it, we could actually get it in under the clock pulse. So this does make it a flip-flop by my definition. Let's see, what else do we have? We have a JK flip-flop here. Um, this is set up a little bit differently. It does have a clock pulse. It's got the J and the K. Oh yeah, no, this over here is actually just telling us. So it is flipping back and forth because they're both high. But it's not doing that anymore once we change them. Set them to both low. It's just holding the state. Set one. Set the other. We set them both. They toggle. We would take the clock and that mechanism out here. It would make it smaller because this in the middle right here, this is because it's what's known as a master-slave logic. I don't like that term, but I haven't seen them change that to like controller peripheral yet. But yeah, so let's see what else we got. Let's see a master-slave flip-flop. I'll just show that. Now it is a D latch with a clock, so it's a D flip-flop. And let's see, what else do we have? Let's see, edge trigger, D flip-flop. It takes it a second because it's got to wait for the edge. Let's see. Yeah, I think we've shown all those. And then counters and shift registers that are made up of them. Let's just quickly look at a 4-bit ripple counter. See, it's going through the numbers. It's essentially counting. Um, and then each of the lines on the counter is connected to one of these JKs. Let's see. Johnson counter, those are always fun. It's just moving 1 bit high through the entire thing here. And then a basic shift register this is a basic 4-bit one. It's just using 4 D flip-flops. It samples at the clock pulse and then moves things along. So there we go. Now see, it'll just keep shifting it down with the clock pulse. U2. Now obviously shift register, I mean it's going to be constantly moving data in theory, but yeah, you could pulse that clock just as needed instead of just letting it go on like this. So let's see. Got a parallel in, serial out. This one's 8-bit, but it's the same idea. Oh wait, yeah, okay. Um, Loader shift. All right, so we're loading 0010 or 2. See, it's just sitting in clock pulse. It's not shifting. Now it's done because the last one in this was an L. If you want to get fancier, you get something like a universal one, which is much more complicated. It actually has to have states, hold, shift left, shift right, load data. It means that it can shift and load data both parallel and serial. We'll be getting to all of this in a future video that'll be dedicated to shift registers. I'll probably even do videos on specific ones. If you want to get really pretty and fancy, let's see, here we go. This is a specific one. So it's got two registers. This is the 595 that you're going to find in a lot of hobby kits. You've got two different types of the flip-flops. The one on the top has a reset signal. The one on the bottom doesn't, but it's as simple as, let's see, set data. Actually, let's clear first. Okay, so the top is storage, or I can't, yeah, okay, shift register dumps into storage, and storage can dump in outputs. So this turns the output on and off. It's an active low. Let's turn it off for a second. Um, let's do, we already cleared. There we go. Let's do high, 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 low, low, low. So we've got 0, 0, 0, 1, 0, no, wait, sorry, 0, 0, 0, 1, 1, 1, 0, 0. Okay. And then we got the latch. It moves it into the storage register. We go active low in the output enable, and here we go. We've displayed our numbers. So there you go for Falstead. Now moving into Simu IDE, we've got some basic generic ICs, or they're displayed as essentially squares or rectangles. Not technically ICs, I suppose, but we've got our D flip-flop, our T flip-flop, our RS, SR flip-flop, and our JK. Each of these are flip-flops. It's not latches because clock signal. Um, but we've got implementations of a couple of different chips. This is an AND-gated JK flip-flop. It's got two different flip-flops here. Let's see, what else do we have? Got dual D positive edge triggered ones. Actually, the and the or and the and, I believe it's essentially one flip-flop, but with multiple J and Ks. I think that's the way it works. Um, I think if it's asynchronous, it has nothing to do with the. Trying to remember some of these. Some of these are chips I don't really use. Let's see. Let's find another example. Shift registers. That's not what I'm looking for. D. This is 8 different D flip-flops with a common clock pulse and a common output. I'm not seeing an SR. Let's see if I put latch in. It will give me. Oh no, there's some stuff for latches here. 8. This is a 4-bit. This is basically uh, yeah, it's a 4-bit bistable latch. Let's see. Oh, oh, hold on. Here is a quad RS latch chip. I think I may actually have this. So it's just 4 simples. There's no clock signal. It's got an enable. Got 4 outputs, so it's pretty simple.